Please kindly confirm audio, video, and screen once. So sorry, I was in journey, so I am taking a bit late today. Fine. So till yesterday, what we have discussed is significance of the inductance placement in the circuit. That's what the thing we have discussed. After that, I said that we will be starting with the single phase 2-wire system inductance calculation. So after that, we will be moving on to single phase, single wire, and then 3-phase system. Okay. So let's start with the single phase 2-wire system. Yeah. So I'm taking up in the next heading, that is inductance calculation for single phase 2-wire system. Inductance calculation for single phase 2-wire system. Yeah. See, I am showing two conductors to you. Maybe I can say phase A and phase B, means forward and return conductors, I can say. So A and B I am showing here. Just observe. So this is conductor A, right? And this was a conductor B we have, let me assume. Maybe of equal size or unequal size, doesn't matter. So this is A and this is B. And conductor A might be having a radius of R1 I am taking up. Conductor B might be having a radius of R2 I am taking up. And distance between these two conductors I am taking up like D, right? So between A and B conductors, the distance I am showing as D. Like this I am showing D. Done. Now, conductor A is having an inductance of LA. Conductor B is having an inductance of LB. Okay, conductor A inductance is LA, conductor B inductance is LB. Could you please tell me how these two conductors are connected? Anybody please tell me? Yeah, we will be finishing the class by 9:30 only. I don't extend further. Beyond 9:30, I don't extend. I will be completing this one by 9:30 only. Okay. Yeah, how these two conductors are connected? Series. For example, if you want to get some sort of feel about this one, you assume that it is one AC voltage source or some voltage source, whatever it is, AC or DC, whatever it is. And this is a forward conductor, you can say it is A. And this is a return conductor, you say it is B. Okay. So then after that, you have some load, doesn't matter. So this is that single phase 2-wire line, what we have shown there. This A and B having inductances like LA and LB, and these two are connected in series. Then obviously loop inductance is nothing but summation of the two. So called LA plus LB we have to write. Okay. So I'll say loop inductance or circuit inductance here. Loop or circuit inductance. So L total, you can write that name, which is nothing but LA plus LB. LA plus LB. Let us concentrate on LA calculation now. Let's concentrate only on LA calculation. Okay. Before moving ahead, means before moving to the calculations of this LA and LB, I want to tell some assumptions. First assumption, I'll write here. Assumptions I am saying here. First assumption is radii, so-called R1 and R2 numbers are very, very low compared to D value. It is very practical one, what we can observe outside. For example, if you see simply some single phase 2-wire system, definitely conductor size looks to be very small compared to distance between the conductors. So R1 is very, very less compared to capital D. R2 is very, very less compared to capital D. So this is the way out, right? The first assumption. Second assumption. See, in the previous chapter, we discussed about different types of conductors, like solid, AAC, ACSR, in that manner. But now, from this point onwards, we are going to proceed our discussion only in the view of the solid conductor. Okay. After deriving the inductance equation for solid conductor, we will extend that for any other type of conductor with some change. Following all of you? Okay. So I'll say here, conductors are assumed to be solid conductors. Conductors are assumed to be solid conductors. Solid in nature. Okay. Next thing. See, I will be assuming that current density as uniform throughout the cross section of the conductor. What is the meaning of this one? Assuming that current density is uniform throughout the cross section of the conductor. What is the meaning of that? Anybody please tell me? We are neglecting the skin effect. Okay, let me write that statement. So next assumption I am writing here, that is current density J is assumed as uniform throughout the conductor cross section. Throughout the cross section of the conductor. Throughout the cross section of the conductor means, in bracket you can say no skin effect, or you can say skin effect was neglected. Skin effect was neglected. So is it a reasonable assumption? Anybody please tell me? Is it a reasonable assumption to neglect the skin effect? Yeah. Is it a reasonable assumption to neglect the skin effect? Yes or no? See, one thing, listen please, listen to my words. Very simple thing I will tell you. Practically speaking, we have some skin effect in the conductors. That skin effect we should take into the electrical equivalent circuit. Yes or no? So already that skin effect we have taken up in the calculation of the resistance. Then tell me, is it required to take again that skin effect into the calculation of inductance and capacitance? Very simple question. We have some skin effect in the conductors that we should consider into circuit. Already we have taken that in the resistance calculation, right? If you have taken it already in the resistance calculation, is it required to take again that in the inductance and the capacitance calculations? Is it required or not? So I don't think so. It's not needed. So that skin effect is neglected is a what you call better assumption to be chosen. Yeah. Next thing. So let's think about this LA, conductor A inductance from this point onwards. So I'm taking up in the next slide. Conductor A inductance. Conductor A inductance. Conductor A inductance. So I'll write LA. The basic formula for this inductance is flux linkages by current. Already we assumed it as a linear one. So I am writing simply it is flux linkages by current. So flux linkages, I'll say psi A by current in the conductor A. What is that current in the conductor A? I will be assuming this current as plus I current. Other conductor is going to carry minus I current. Maybe if you want me to show that plus I and minus I in this diagram, I'll show this current as plus I and this current as minus I. Because the current is flowing in the reverse direction. But I want to take currents in same direction. In the diagram, I want to take it in the same direction. So I have taken first one as plus I, second one as minus I current. Okay? Yeah. So let's proceed. So in the denominator, I will be keeping this I. So psi A by IA, or you can say it is simply current I. Okay. Now, listen. So yesterday, we said about flux linkages, right? Flux linkages in a conductor. We are dividing that into two parts. One is the internal, occurring inside the conductor. That is called as internal. Second one is external, occurring outside to the conductor. So I'll say psi A is divided into two parts. One, internal linkages. Next one is external linkages. So I can write here. Psi A is getting divided into two parts. First one, internal linkages. Second one will be external linkages. You write simply internal means occurring inside the conductor. And psi external means occurring outside the conductor. Occurring outside the conductor. Occurring outside the conductor. And resultant is nothing but summation of these two, internal plus external. So such that psi A is nothing but internal linkages plus external linkages. And now if you talk about inductance LA, which is a psi internal plus psi external, so called psi A, by current is I. Current is I. Okay, so this we can rewrite as psi internal by I, one term, plus second term is psi external by I. Two terms here, na? First term is psi internal by I. Second term I am saying is psi external by I. And that psi internal by I, we can say as L internal, and psi external by I am going to call it as L external. First term I am saying internal inductance. Second term we are going to call it as external inductance. Okay. So I am not going for any derivations here. I'm not going for any derivations. Directly, I will be giving you the expressions for that L internal and the L external terms. Okay. Yeah. You please complete this one quickly. I will move to next slide. Complete this one quickly. I will move to next slide. So I think you have done. So I'll say here, internal inductance. First term I am saying here, internal inductance. Inductance. L internal is equal to L internal equals to. So I'm saying formula directly, as I said you, I'm not going for any derivation. It will be like mu naught into mu r by 8 pi. L internal is equals to mu naught into mu r by 8 pi. I'll come to each and every term in that formula. Second one, external inductance I am writing. External inductance. Okay. So L external is equal to mu naught into mu r by 2 pi. Mu naught into mu r by 2 pi into natural logarithm of. I'll write what we have to keep in that natural logarithm of. Okay. So I will tell briefly about the inductance calculation, the procedure of the inductance calculation. Okay. So I will move to the next slide. To discuss about it. Just listen. See, we have two conductors as we have taken. This is a conductor A with some radius of R1. Beside to that, we have this conductor B, and this is a conductor radius is R2. Distance between these two conductors, center to center gap, that is a D. Center to center gap is D, I am sure, like this. Okay, listen. All of you stop writing and just listen to my words. See, actually, we said the formula for inductance as flux linkages by current. L is equals to psi by I. Okay. L is equals to psi by I. That's the formula for inductance. What is flux linkage formula? Anybody tell me please, what is psi formula? What's the formula for psi? That is number of turns into flux, you can say. Psi formula will be number of turns N into flux phi. Okay. What is flux formula? Anybody please tell me what is the formula for flux? Flux density into area. B into area. Okay. What is flux density? This is mu into H. Flux density is nothing but mu into H. Okay. What is H here? How to find out that H? Anybody please tell me how to find out that H? That H we are going to find with the help of Ampere's circuital law. We are going to find that H equation by means of Ampere's circuital law. After getting that H equation, that we will substitute in B, and then phi, and then psi, and finally we get the inductance L. So this is a reverse way what we have discussed till now, and actually this is a way of calculating that inductance formula. That's the way of calculating the inductance formula. So that H we have to calculate by using Ampere's circuital law. Okay. See what that Ampere's circuital law will tell you. What that Ampere's circuital law will tell you. Simple, simple. I am writing that here. Circular integral H bar dot dl bar. Circular integral H bar dot dl bar is equal to current enclosed. Current enclosed. Circular integral H bar dot dl bar is equals to current enclosed in that circle what we have chosen. That's the meaning here. Simple. So first you should take one circle. First you should take one circle, and how much amount of current was enclosed inside that circle? How much amount of current was enclosed inside that circle? That will decide the magnetic field intensity H value. Following all of you. Now, very simple thing. Just listen. I'm taking up number of circles. What's the difference between phi and psi? Phi is a flux, Shiva. Phi is a flux. Psi is a linkages. It is flux. Okay. And this is flux linkages. Flux linkages. That's the difference. Why not taking d psi by di? Shahil already we said it's a linear inductor, right? Linear inductor. That's why I'm going directly psi by I, as it's the linear inductor. Yeah, let me continue. Let me continue with this. I'm taking one small circle. Just tell me how much is the current enclosed. First of all, I want to tell you this conductor A current is plus I. Conductor B current is minus I. Conductor A current plus I. Conductor B current is minus I. Just observe now. Observe. This is one circle I am showing. This is one circle. Okay. To calculate H value on this circle. To calculate H value on this circle, we should check how much amount of current was enclosed. How much amount of current was enclosed? How much it was enclosed? Is it current I or less than I or more than I? Anybody please tell me. Inside that blue color circle, what I have shown there, how much amount of current was enclosed? Is it less than I or more than I or equal to I? Definitely less than I. Definitely it will be less than I. Yes or no? Okay, next thing. See, I am taking up one circle here like this. One more circle I am taking like this. And I want to calculate H value on this circle. I want to calculate H value on this circle. Okay. How much amount of current was enclosed inside the circle? How much amount of current was enclosed inside the circle? That will be total current I. Definitely, it will be total current I. Okay. Next. Similarly, listen to my words. I am extending the circle. I am extending the circle till the point where the conductor A shows its complete effect. Listen my words. I'm extending that circle up to the point where the conductor A shows its complete effect. Maybe I'll take one more circle here. Let us say, tell me now, what is the value of current deciding the H value here? What is the value of current deciding the H value here? Again, current enclosed. What is the current enclosed? That will be conductor A current only. Conductor A current only. Now, just listen. Just listen to this. Listen to this. Listen to this. And I calculated H value on the surface, on the circle, which is decided by current of conductor A. I current is deciding that. Okay. After calculating H value, let me go for B, phi, psi. What is this psi indicates for you? What is it psi indicates means those are the flux linkages. Those are the flux linkages occurring inside the circle, inside this circle. Flux linkages occurring inside the circle created by conductor A current. Created by the conductor A current. That's the meaning of it. For angle of you. So in the same way, I am extending the circle and finally I have reached to this point, let us say. 1 minute. Okay. I'm reaching to one point, something like this. Touching to conductor B. Just touching. just touching to conductor B. Could you please tell me now, if I have taken that much big circle, big circle, if you want to calculate H value here, who will decide that H value again? Current enclosed inside the circle. What is that current? Conductor A current only, na? That will be simply conductor A current only. After taking up that conductor A current, I'll calculate H value, B value, phi, psi. That psi is a flux linkages produced by that conductor A current as a whole inside that big circle what we have chosen. I think all of you getting this point. Is it okay for you? Tell me please, is it okay? Now the thing is, if I am crossing that circle, what will happen? For example, if I go something like this, if I am cutting that conductor B, what is that current enclosed now? What is that current enclosed? Is it I or less than I? Definitely less than I, because some portion of B current is going to cancel the A current. Following all of you means my intention is to tell you to calculate, listen please, to calculate flux linkages produced by only conductor A. To calculate the flux linkages produced by only conductor A, we have to extend our ampere loop up to what point? We have to extend our ampere loop up to what point means up to surface of conductor B only we have to extend it. I don't know. Are you clear about this or not? Very simple point. We have to calculate H value, or we have to calculate flux linkages produced by conductor A. Okay. Up to what length this conductor A will show its effect. That we have to know. That is only up to the surface of the conductor B. If you are crossing that surface, conductor B current is cancelling that conductor A current in the loop. So the resultant flux linkages are not the linkages produced by the conductor A alone. Conductor B is also participating beyond that surface of conductor B. That's why we will take only up to surface of the conductor B. Yeah, all of you clear? Yes. Yeah, clear? I'll write. So conductor A will have its flux linkages production up to surface of B. One more thing. Inside this blue color big circle, I have again two portions. One is the internal linkages produced by the conductor A, psi internal, occurring inside the conductor, psi internal. And in this portion, we have the psi external. Let me assume this as a center. Means center of the circle A, means conductor A is a center. 0 also. 0 to R1. What linkages we have? 0 to R1. What linkages we have? Internal. That is inside the conductor, right? 0 point I am considering as a center of the conductor A. So 0 to R1, it is inside the conductor only. We get the internal. Okay. Starting from R1 up to surface of B. Up to surface of B means, what is that surface of B length here? What is this length? Anybody tell me? It will be D minus R2. That will be D minus R2. Yes or no? Not R1 plus D. D is center to center gap, right? D is center to center gap. So it will be D minus R2. D minus R2. So from R1 to D minus R2, we have the linkages as external linkages. Clear? Now, in that external inductance formula, we used to get a term like in the natural logarithm d minus R2 by R1. This type of term you are going to get in that external inductance calculation. D minus R2 by R1. This type of term you are going to get. Okay. So external linkages starting from surface of the conductor A up to surface of B. Okay. Inside the conductor A, we have the internal linkages. I think all of you getting this. So this is sufficient for this thing, and we will be continuing with only internal and external linkages from this point. So I am moving back to the previous slide. Let me tell about this, what we call notations and all. What is mu naught here? What is mu naught? Mu naught is equals to 4 pi into 10 power minus 7 Henry by meter. Mu naught value. Okay. Permeability. Permeability of free space, or you can say vacuum. That is 4 pi into 10 power minus 7 Henry by meter. Mu r is a relative permeability. Mu r is a relative permeability. Relative permeability of what? Relative permeability of what? Anybody please tell me? Relative permeability of the material over which we get the internal linkages. Relative permeability of the material over which we get the internal linkages. Where we are getting the internal linkages? Inside the conductor. So this mu r is a conductor relative permeability. Is a conductor relative permeability. Conductor relative permeability. And 8 pi is a constant number. 8 pi is a constant number. And this units, if you observe, it will be Henry by meter. Units will be like Henry by meters. Okay. Next, external inductance you check now. External inductance you check. Sir, but there will be flux linkages external for B also in the big circle touching B. Yeah, Satvik, just check about only conductor A effect up to what point. If you are considering conductor B, it will be taken up to surface of A. If you are taking conductor B effect, it will be taken up to surface of A. Yeah, good. Next thing. The external inductance, mu naught, say 4 pi into 10 power minus 7. What is this mu r? Mu r is the relative permeability of the medium over which we get the external linkages. So this you can say for surrounding medium of the conductor. What is the surrounding medium of the conductor? That is air. This is for air. Of course, you know, for air, mu r is equals to 1. For air, that relative permeability is equals to 1. Okay, let's say 2 pi constant. And ln of d by r1, it will be a unitless number. Numerator in meters, denominator also in meters. And overall units will come to be Henry by meter. Good. Now, just I will join these two equations, L internal and L external together. That I am going to say simply as LA. Okay. So I'll write in the next slide. Writing the next slide. So LA is equals to L internal mu naught mu r by 8 pi plus L external mu naught mu r by 2 pi natural logarithm d minus r2 by r1. Okay. So this units will be Henry by meter. Units of this will be Henry by meter. And the first mu r is for conductor and second mu r is for air. First mu r is for conductor, second mu r is for air. But you know, already in the assumptions we said that will be this derivation in EMF. No. We don't get this derivation in EMF. Sir, here flux linkages linking with only conductor are considered right. But external air gap flux linkages are taken. Yeah, we have taken up external linkages also, right? Internal linkages are the linkages occurring inside the conductor. Please tell me, how is the value of R2 compared to D, I said? R2 is very, very less compared to D now. So obviously, this D minus R2, whatever we have, that I am going to take it as D only. That we are going to take it as D only, so that you can write LA LA like mu naught into mu r by 8 pi. Mu r is for conductor here. Plus this mu r is 1. We said for air. So it is mu naught by 2 pi. Mu naught by 2 pi. Natural logarithm. It is capital D by R1 in terms of Henry by meter. And you write this mu r is for conductor. That mu r is for conductor. Okay. Now, let's consider the material. What material we are using for yeah, see, most of you are having a doubt about this one. Kindly listen. I want to take from surface of this conductor to surface of this conductor. Na? I want to take from surface of this conductor A to the surface of the conductor B. Okay. See, this radius is R1. Two circles here. First circle radius is R1. What is second circle radius? You should measure from center of this only, right? Because we assumed this as 0. From this to this point, if you are measuring, see, center to center gap is capital D. Center to center gap is capital D. Now I am measuring from center of A to surface of B. Center of A to surface of B. Only that R2 value has to be deducted from D. How R1 will be deducted again? So it will be D minus R2. So it is starting from circle R1 radius to circle D minus R2 radius. Okay? Getting Naveen? Yeah. So conductor is of made by aluminum, and that aluminum material is also having the relative permeability as 1, and we will keep that, and we will try to modify this equation LA further. Okay. So for aluminum conductor, aluminum or copper, aluminum or copper conductors, relative permeability is equals to 1. Therefore, LA will come to be mu naught by 8 pi plus mu naught by 2 pi into natural logarithm D by R1 in terms of Henry by meter. Okay, next. You take that mu naught by 2 pi common. I'll come to the mutual inductance and all. Just listen to the thing what I'm saying you. Sir, but if R1 is included, then internal linkage. Shiva Prasad, just go through it, what I'm saying you. I am taking from R1 to D minus R2. Where is that R1 included? 0 to R1 is a internal. 0 to R1 is a internal. Second calculation, we are starting from R1 only. So 0 to R1 was already removed. Okay. Why we considered this as approximately D? Because radius is very low compared to distance between the conductors. Okay, let me simplify this equation. We have two terms. I want to combine these two terms together. I want to rewrite it as a single term. Okay, so I'll take that mu naught by 2 pi common here. Mu naught by 2 pi common. And by taking that mu naught by 2 pi common, you get here 1 by 4 plus natural logarithm of D by R1 in terms of Henry by meter. And we want to push this 1 by 4 into natural logarithm. I want to move this 1 by 4 into the natural logarithm. That mathematical modification we are going to take up further. Okay. So I'll show in the next slide. Next slide. LA will be equal to mu naught by 2 pi into, we have 1 by 4, na? 1 by 4. That 1 by 4 we are going to write as ln of e power 1 by 4. If you write like that, it will be 1 by 4 plus ln e. Ln e is 1, so it will be simply 1 by 4. Plus, we have ln of d by r1. D by R1 in terms of Henry by meter. And you add these two natural logarithms together, like ln of A plus ln of B equal to ln of A into B. Ln of A into B. So you can write this like mu naught by 2 pi natural logarithm. You get a term like D by R1 into e power 1 by 4 in terms of Henry by meter. E power 1 by 4 is a constant number. E power 1 by 4 is a constant number. Yeah. Listen, please. Listen. See, actually, if you look at this equation, we have two terms here. One is internal, mu naught by 8 pi. Next one is of external, that is mu naught by 2 pi into ln of d by r1. Internal, external. See, whenever we are adding this internal term to external, whenever we are adding this internal term to external, inside this natural logarithm, we are getting like d by r1 into e power 1 by 4. D by r1 into e power 1 by 4. Simple. Okay. Now tell me, with what I have to attach this e power 1 by 4 constant? With the distance or with the radius? With what term among these two I have to attach this e power 1 by 4? Is it with distance or radius? By common sense, I can say we can go with the radius. We can go with radius. Why it is so means internal term is a conductor term, right? Internal term is a conductor term. So after adding this, we are getting the d by r1 into e power 1 by 4. So as it's a conductor term here is a radius. That's why we are attaching that to radius. Okay, so this we can rewrite. This we can rewrite as mu naught by 2 pi natural logarithm. Just look this, d by r1 into e power minus 1 by 4 Henry by meter. That r1 into e power minus 1 by 4, it will be coming as a number like 0.7788 into r1. 0.7788 into r1. Okay? 0.7788 into r1. And this we will write shortly. This will write shortly as r1 dash. R1 dash. And this we are going to call famously as GMR of the conductor. Geometric mean radius of the conductor. This we are going to call as GMR of the conductor. A. Geometric mean radius of the conductor. It can be called sometimes as imaginary radius of the conductor, or you can say fictitious radius of the conductor. So it can also be called as fictitious radius of the conductor. Fictitious radius of the conductor. Imaginary radius, or you can say this as a fictitious radius of the conductor. Okay. So let me rewrite this LA equation now. LA equation we will rewrite as mu naught by 2 pi natural logarithm d by r1 dash. D by r1 dash. It's in Henry by meter. Henry by. Please complete it. I will ask one very simple question to you. One very simple question. This is one confusion, or you can say some clarity needed. Just listen. So I will show two conductors to you, identical shape conductors. For example, you see this is conductor 1. Same conductor I will repeat. Just try to observe what I am saying. Both are having a radius of r. Both the conductors are having a radius of r. In the first case, I will show some portion. Second case also, I will show some portion. My question is, which portion is going to be called as GMR? Which portion among the two is going to be called as GMR? First, let me show it. I am showing the first portion, something like this. This is a portion what I am highlighting. Okay. This red color portion, and red color portion, it's a circle, of course, and that radius is a 0.7788 into small r dash, and second one, In the second case, I am showing some red color portion like this. Outer portion I am showing. In the second case, I am showing the outer portion. Okay. And this thickness is R dash. This red color portion thickness is R dash. 0.7788 into smaller. Okay. My question is, which portion is going to be called as GMR among the two? Among the two, which portion is going to be called as GMR? Anybody? First one or second one? First one or second one? No one. No one of these two is going to be called as GMR. Why? Why you are saying second one? Or somebody is saying first one? Why? Why it is so? See, already I have given that name, right? Imaginary radius of the conductor or fictitious radius of the conductor. What do you mean by this imaginary or fictitious radius? Which we can't show physically. Which we can't show physically. All of you getting my meaning? Right? So, see, actually GMR can't be shown exactly in the conductor. In the conductor, which portion is going to be called as GMR means we can't say that. GMR is a pure mathematical term. GMR is a pure mathematical term. How you are getting this GMR in the calculation means simply by the addition of internal inductance to external inductance, I am getting a term like GMR. Following all of you. So GMR does not have any technical significance at all, right? It does not have any physical significance at all. It is simply a mathematical term coming in our derivation. Following all of you, this clarity you should have. This clarity you should have. Okay? Yeah. So I'll write that statement what I said. No one of these areas or portions are called as GMR. No one of these portions called as GMR. No one of these portions are called as GMRs. GMR does not have any physical significance. Any physical significance. Okay. GMR does not have any physical significance. It is a purely mathematical term. Purely mathematical term. Is purely mathematical term. Sir, can we say that external flux is more than internal flux because of effective LA? Yes, correct. Satvik, yes. Yeah, very simple, Sangeeta. GMR is a term which is coming only in the mathematical derivation. There is no technical significance for that. So that I can't show the GMR exactly in the conductor, which portion. Right? Fine. Tell me out, tell me. Do you have any relationship between skin effect and GMR? What is skin effect? Skin effect is a pure technical term. Skin effect is a pure technical term. What we'll say, skin effect means it's a tendency of alternating current to be concentrated nearby the surface of the conductor. Okay, and we will be showing that the conductor is concentrated, sir, current is concentrated nearby the surface of the conductor. So, fine. So, skin effect is having a physical significance and it's a technical term. And we don't find any relationship between that skin effect and the GMR. Okay, this clarity you should have again. Following all of you? Is it okay? Skin effect is a technical term. It has its physical significance. GMR won't have it. Okay, sometimes maybe in the examination, they will ask you one question in this way. Just listen. For example, yeah, could you please tell me, first of all, whatever the derivation we have made, so-called inductance calculation we have done, is it by neglecting skin effect or by considering skin effect? This calculation, this LA formula what we have derived, is it including skin effect or neglecting skin effect? after neglecting skin effect. After neglecting the skin effect. Okay. If skin effect is considered, listen to my words, please. Listen to my words. Skin effect is considered and it is maximum. Skin effect is considered and it is maximum. In the sense, we don't have current flow inside the conductor at all. We have the current concentration only on the surface of the conductor. In that situation, how will be this inductance formula? How will be this inductance formula? Following? Yeah, let me write. It is a bit important question, particularly in objective examination sometimes. Just listen. If skin effect exists, or is considered, and it is maximum. And what we should say? Then we don't have any current inside the conductor. No current exists inside the conductor. See, if we don't have any current inside the conductor, what will happen to the internal linkages? Yeah, kindly listen. Listen to this question, Gopal. Don't question that question what I am asking you. Tell me, please. 0. We don't have any internal linkages. Then what about psi A? It will be only external. Then what is LA? That will be only external. So it will come to be mu naught by 2 pi ln of d by r1. That's it. D by r1 in terms of Henry by meter. Yeah, when the inductance value is more now, when the value of inductance is more, is it with skin effect or without skin effect? When the value of inductance is more, is it with skin effect or without skin effect? Without skin effect, inductance value was more because of the internal addition. After considering the skin effect, inductance value may be a bit less because I don't have any internal term in the calculations. Okay, so if you want, I'll write here LA without skin effect will be greater compared to LA with skin effect. LA without skin effect is greater compared to LA with skin effect. Okay. So, but as far as examination is concerned, always we have to use this formula only for the inductance calculation. We should not neglect that 0.7788. You should consider that 0.7788 and we have to go for the calculation of the inductance. Okay. So let me continue with this formula only. LA equals to mu naught by 2 pi into ln of d by r1 dash. We'll extend it little bit. Then we'll write for LB. Then we'll take the loop inductance and we will conclude it. Okay. Yeah. So let's move ahead. So LA equation, we have already mu naught by 2 pi. So here you keep this whole in a bracket. Keep it aside completely from our discussion. Because this is not the thing what we are discussing, right? Keep it aside from our discussion. So in the discussion of inductance, formula is mu naught by 2 pi ln of d by r1 dash in terms of Henry by meters. And that mu naught you can keep 4 pi into 10 power minus 7. Mu naught you can keep it as 4 pi into 10 power minus 7 by 2 pi, and you can get this like 2 into 10 power minus 7 natural logarithm d by r1 dash Henry by meter. 2 into 10 power minus 7 ln of d by r1 dash in terms of Henry by meters. And I'll write this like 0.2 into 10 power minus 6 natural logarithm d by r1 dash Henry by meter. Like this you can write 0.2 into 10 power minus 6 ln of d by r1 dash Henry by meter. The 10 power minus 6 you take aside. You can write it as microhenry by meter or millihenry by kilometer, any word. Microhenry by meter or millihenry by kilometers. So generally, we use to measure the length of transmission line in kilometers. That's why I will write it as millihenry by kilometers. 0.2 ln of d by r1 dash millihenry by kilometers. Clear? Next thing. Let's take up the conductor B also and we will conclude it. Conductor B. Conductor B. What is LA formula for conductor B? Same equation. 2 into 10 power minus else you write this one. 0.2 ln of d by r1 dash. 0.2 LB. 0.2 ln of dy. In place of r1 dash, you can write it as r2 dash. 0.7788 into r2 in millihenry by kilometers. Okay, so that is a conductor B inductance. Conductor B inductance. Now you take up the loop inductance here. Loop inductance. Loop inductance. I'll write in different ways here. L total, which you have LA plus LB. LA plus LB. And that LA, I'll write in Henry by meter for time being. After that, we get in millihenry by kilometer also. I'll write in Henry by meter. Henry by meter. LA, you know already 2 into 10 power minus 7. Natural logarithm d by r1 dash. Henry by meter plus second one is 2 into 10 power minus 7 natural logarithm d by r2 dash in terms of Henry by meter. Now you add these two together, we'll get L total. Do that calculation, do that addition. This mu naught value 4 pi into 10 power minus 7 I have mentioned already. That by 2 pi will give this one. So let's continue with this 2 into 10 power minus 7 is common. So ln of A plus ln of B like that you get. So let's write L total. 2 into 10 power minus 7 that is common. We have ln of d by r1 dash into d by r2 dash. So it is d square by r1 dash into r2 dash, you can say. D square by r1 dash into r2 dash. I will try to rewrite this. I'll try to rewrite this one in a standard domain. In a standard domain, you can take it like 2 into 10 power minus 7 natural logarithm. Just observe, I'm rewriting this d square by r1 dash into r2 dash term. D by r1 dash r2 dash square root. D by r1 dash r2 dash square root whole square Henry by meter. Like this you can write. D by root of r1 dash r2 dash whole square Henry by meter. The 2 we will take to the front of natural logarithm. So it will come like 4 into 10 power minus 7 natural logarithm d by root of r1 dash into r2 dash. This in terms of Henry by meter. D by root of r1 dash into r2 dash in terms of Henry by meter. If you want to write it in millihenry by kilometer, you can take it as 0.4 natural logarithm d by r1 dash into r2 dash millihenry by kilometers. Millihenry by kilometers. Okay. So let's continue. If both conductors are identical, so called if R1 and R2 are equal, then obviously LA and LB are equal. Let me write quickly. If both conductors are identical, means R1 equal to R2, let us say it is R. Then LA equal to LB equal to 2 into 10 power minus 7 natural logarithm D by R dash Henry by meter. L total is LA plus LB, so it is 2 times of LA. So it will come 4 into 10 power minus 7 natural logarithm D by R dash in terms of Henry by meter. Like this. Simple, simple. Okay, done. Next. Next thing. See, whatever the LA formula we have now, LA, I'm going to divide that into two parts. Maybe this equation you consider, this equation. 2 into 10 power minus 7 ln of D by R dash you consider. See, in this formula, you observe definitely that the inductance value depends upon two things. Inductance of conductor A you talk. Inductance of conductor A depends upon two things. One is a distance between conductor A to conductor B. Distance between conductor A to conductor B, one thing. Next one is a radius of the conductor. Next one is a radius of the conductor. See, I will divide this inductance into two parts. Divide the inductance into two parts. One part depending only on the radius of the conductor. Second part depends upon the distance between the conductors. Okay. So whichever the term depends only on the radius, I will be calling that as self term. Self term, self. Whichever the term depends upon only distance between the conductors, we call it as a mutual term. Mutual between conductor A to conductor B, or you can say forward to return. Okay. So I'm rewriting that LA. 2 into 10 power minus 7. First term is ln of 1 by R dash. Ln of 1 by R dash. That's the first term. Second term. Listen please. Second term. Don't write. Just listen. Plus 2 into 10 power minus 7 natural logarithm D. Rather than writing that as D, I will keep that as 1 by D in a standard notation. 1 by D, and here I will be showing that minus sign. 2 into 10 power minus 7 ln of 1 by R dash minus 2 into 10 power minus 7 ln of 1 by D in terms of Henry by meter. In terms of Henry by meters. Getting. So first term we are going to call it as self term, or you can call sometimes as self-inductance of the conductor A. Self-inductance of the conductor. Self-inductance of conductor A. And this we are going to call as a mutual term, or you can say mutual inductance between conductors A and B. Mutual inductance between A and B. Between A and B. Yeah, units, sometimes I'll write millihenry by kilometer, sometimes I'll write Henry by meter. Henry by meter. Kindly observe. If I write 2 into 10 power minus 7, I will be going for Henry by meter. If I write simply 0.2, I will be keeping millihenry by kilometer. That you have to think what I am writing here exactly. Okay. Now, I'll call this term simply LS. This self-inductance I'll call LS. And this mutual inductance let me call as LM. Mutual inductance as LM. And you observe now, self-inductance is proportional to, or self-inductance proportional to ln of 1 by R dash. 1 by R dash. That R dash is going to be called as self-distance. R dash is going to be called as self-distance. Whereas mutual inductance is proportional to ln of 1 by d, and the d is going to be called as mutual distance. Okay, so I'll show in the next slide. Next slide. Self-inductance is proportional to ln of 1 by r dash. That r dash is going to be called as self-distance. And mutual inductance is proportional to ln of 1 by capital D, and that capital D is going to be called as mutual distance. Mutual distance. Okay. See, for example here, if you have two conductors, one beside the other, it's a conductor A, conductor B. Maybe it's a single phase two-wire system only we are talking. Single phase two-wire system only. This is a way how we have to familiar with this now. Again, I'm saying you. Just listen. I will revise it quickly. Just have a look at this. What I am saying you. Yeah, I'll repeat it. Yashwant, kindly listen to me. What I'm saying here first. This is carrying a current of plus I in this direction. Second conductor current also you should take in the same direction. Same direction you should take. You keep it as minus I. Keep that as minus I. Okay. So I'm keeping this current as minus I. Fine. Next. Conductor A is having a self-inductance of Ls. Conductor B also having a self-inductance of Ls. Between these two, we have a mutual inductance of Lm. That's the thing what we have seen till now. Self-inductance, self-inductance. Mutual inductance between the two conductors as Lm. Okay, now, what is the expression for? What is the expression for, or what are the flux linkages? Flux linkages experienced by conductor A. What are the flux linkages experienced by conductor A? Psi A. Psi A. Say, listen, please, listen. Don't confuse. I will give a clarity to you by using a problem also. Just listen, follow this. See, as far as this diagram is concerned, flux linkages of conductor A means first I should take self linkages, next I should take mutual linkages. What are the self linkages? Inductance into current is one formula. Inductance into current is one formula for flux linkage. Yes or no? Okay. What is it now? Ls into I. Ls into I is a self linkages of conductor A. Self linkages of conductor A. Ls into I. Okay. Next, mutual linkages from conductor B to conductor A. Mutual linkages from conductor B to conductor A. That is nothing but mutual inductance into conductor B current. Mutual inductance into conductor B current. See, you know, Ls into Ia is nothing but I, and plus Lm into Ib value was minus I. So you take that current I common, which is conductor A current only, and ultimately you get this like Ls minus Lm. This is the inductance of the conductor A. Net inductance of the conductor A. Net inductance of the conductor A. Yeah, all of you getting this? Sangeeta, one conductor is carrying current in one direction. Second conductor is carrying current in the opposite direction. Opposite direction. So I have taken that current as minus I in the same direction. Getting all of you? Please tell me. Clear? Good? Good. Very simple thing. So actually, all of you listen. There are two classifications for flux linkages. There are two classifications for the flux linkages. First one, internal, external. One classification with what we have started. Yes or no? Internal, external is one classification with what we have started. And after deriving the equation of inductance by using these linkages, internal plus external I got. Internal inductance formula I have taken. External formula also I have taken. And I have added them together. And we consider the conductors as aluminum or copper conductors. and mu r is 1 in both formulae, and added both equations together, and finally we get LA formula something like this. Okay, and then we discussed about the GMR, fictitious, radius and all, and then we have moved to the resultant equation of inductance of conductor A. Same thing we have extended for the conductor B, and we have gone for the loop inductance. Okay, then if both conductors are having equal radius, LA, LB are exactly equal, and obviously L total equals to 2 times of L. Then that LA we are dividing into two parts as self and mutual. Self is a term which depends upon the conductor dimension. Mutual is a term which depends upon the distance between the conductors. Okay, so then we have gone for this type of thing where I said we have again a classification of flux linkages like self and mutual. Self and mutual. Ultimately, the result will be same. Result will be same. Yeah. Getting good. Now we'll take some simple problems in this single phase system inductance calculation. So after that, we'll move on to extension of this. So called GMR we discussed, self distance we discussed a little bit. After that, I will concentrate mainly on the mutual distance calculation. Yeah. So let's take up one problem. So you please go through it. This one. The self-inductance of a long cylindrical conductor due to its internal magnetic flux linkages is K, Henry by meter. If the diameter of the conductor is doubled, then the self-inductance of the conductor due to its internal flux linkages would be how much? Due to its internal flux linkages would be how much? Check this now. Yeah. See this first of all. See, they have given self-inductance of conductor, okay, but they have added one term like self-inductance due to internal linkages. Self-inductance due to internal linkages. For time being, you keep this problem aside. You keep this problem aside. Think about the thing what I am discussing now. Okay? Yeah. So in the solution, if I take inductance of any one of the conductor, LA, I'll go with the original formula, internal plus external. Going with the original formula, internal plus external. What is the internal formula? Internal formula is mu naught into mu r by 8 pi. It's the internal. All of you getting this? External formula I am writing. External formula plus mu naught into mu r by 2 pi. Ln of d by r. Ln of d by r dash will not come. 0.7788 r will not come. Why? Because already we have taken internal separate. Yes or no? So you get ln of d by r. That ln of d by r I am writing by ln of 1 by r, one term, and the next term is minus mu naught into mu r by 2 pi ln of 1 by d. Is it okay for you? Is that okay? Anybody having a doubt about it? Is it clear? I have not written anything new. Just we have a basic formula of internal plus external. I have rewritten it in this manner. It will be in Henry by meter. Henry by meter. Could you please tell me? Of course, you know, the first term is due to internal magnetic flux linkages. Can be called as internal inductance. Due to internal linkages. Second term, third term, these two are due to external linkages. Due to external linkages. Okay. I'm asking one very simple question to you. Yeah. Very simple question to you. Please tell me. Please tell me. Yeah, I'm saying, Kavya, why you are not considering R dash? Already I said no, Kavya. Internal plus external. After adding internal to external, we get a term like R dash. But I am writing separately here. How you get R dash again? Okay. So internal I have taken separately. External I have taken separately. So you don't get 0.7788 into R. Okay. Tell me, which is self and mutual here? Anybody? Which is self and mutual? Self. Which is self here? Which is self? First two terms summation. First two terms summation is self. Self is what? Self-inductance formula. 0.2 ln of 1 by R dash, right? 2 into 10 power minus 7 ln of 1 by R dash. 1 by 0.7788 into R you have to write. But you have only R here. So how to get 0.7788? We have to add first term to the second term. After adding these two, we get R dash, and this whole term is going to be known as self-inductance. So first two term summation is going to be called as self-inductance. And the next term is only depending upon the distance between the conductors, it is called as mutual inductance. Mutual inductance. Okay. Next, tell me, what is this first term alone? What is this first term alone? Is it self or mutual? Is it self or mutual? Self due to internal linkages. Self due to internal linkages. L self due to internal linkages. What about the second term? Second term, self or mutual? Self due to what? External linkages. Okay. Self due to external linkages. Last term is mutual due to external linkages. Due to external linkages. Okay. Now the question is what they have asked in the problem. The self-inductance of the long cylindrical conductor due to its internal magnetic flux linkages is K. Because of the internal magnetic flux linkages, he is saying that self-inductance is the value K. Means self-inductance due to internal linkages is a term mu naught mu r by 8 pi. This number he is saying as K. This number he is saying as K. And he is saying that if the diameter of conductor was doubled, what will happen to this number? It is independent on the diameter of the conductor. Self-inductance due to internal linkages is independent on diameter of the conductor, or you can say radius of the conductor. Diameter of the conductor, or you can say radius of the conductor. So your answer will be remains K only. So correct answer from the options will be obviously B. It will be remains K. Remains K. Okay. See this. Same question I am asking you. Self-inductance of a conductor. This I have removed. Is K Henry by meter. If the diameter of the conductor was doubled, then what will be the self-inductance value? Self-inductance of the conductor would be, what will happen? Tell me anybody. Will it be remains at K or increases or decreases? Tell me. Changes or not? Changes or not? Tell me please. Definitely changes. Increasing or decreasing? Increasing or decreasing. If the diameter of the conductor is getting doubled, means radius will be getting doubled. Radius will be getting doubled. So if the radius is getting doubled or radius is increasing, self-inductance value starts decreasing, we can say. Okay. So in this, for this, in the solution, what you can say simply is self-inductance equal to 2 into 10 power minus 7 natural logarithm 1 by 0.7788 into radius of the conductor in terms of entry by meter. And he's saying that radius of conductor was increasing. Because of that, we can say natural logarithm value will decrease and self-inductance will be decreasing. Okay. So LS reduces. Self-inductance value reduces. How much decrement means I can't say. How much decrement in the sense we can't say exactly. Exactly we can't say. Okay. So for that you have to extend a little bit more. Little bit more you have to extend. That 1 by 2 term will come and there was an increment. Okay. So that you should take care. Yeah. Next thing. The question again here is, why this self-inductance due to internal linkages is independent on the diameter? Why it is coming as independent on the diameter? Anybody? Anybody tell me why it is coming independent on the diameter? Reason for this. Reason. One simple option, what I'm going to tell here is that is one of the assumption we have made. Because of one of the assumption, we are getting this as independent on the diameter. Can you guess what that assumption we have made? No skin effect. No skin effect. Or J is assumed as uniform throughout the cross section. By making that assumption only, I can say this self-inductance due to internal linkages is independent on the diameter. Assumption is, sorry, reason is J is assumed as uniform. Assumed as uniform throughout the cross section. Throughout the cross section. Throughout the cross section. Okay. Yeah. Next. Next, we'll take one more formula. Sir, one more problem. One more problem. Just check it. So kindly follow this problem. See this. So a single phase two wire system has inductance value of each wire 1.1 millihenry by kilometers. 1.1 millihenry by kilometers. If the inductance value was increased by 5% by increasing the spacing between the conductors, whereas the radius of the conductors are kept as constant, the increment in the distance is dash percentage. Increment in the distance is dash percentage. Simple, very simple thing. Just go through it. See, is saying that inductance of each wire is 1.1 millihenry by kilometer. Inductance value was increased by 5%. So I'll take this in two cases. Case 1, without increment in the inductance. Case 2, after increasing the inductance. Case 1, I'll say. Case 1. So you take conductor something like this. It's a conductor A, conductor B. Both are having equal radius. You consider distance between the two conductors. I'll take D1 because distance is only the value what we want to increase, right? So D1. Inductance of conductor A, I'll say LA1, which is 1.10 millihenry by kilometers. 1.10 millihenry by kilometers. Okay. What's the formula for LA? What is the formula for LA? That is in millihenry by kilometer, right? Millihenry by kilometer. 0.2 natural logarithm capital D by R dash. Capital D by R dash. This D1 by R dash in terms of millihenry by kilometer. And LA1 number already you know 1.1. 1.1. Next, case 2. Case 2. See, he is saying that inductance value is going to be increased by 5% by increasing the distance. Let's take the distance as D2 now. It is a conductor A and this is a conductor B. Radius is R here. Distance between the two conductors is D2. Now, inductance of this conductor LA2 will be equals to 5% more compared to LA1. 5% more compared to LA1 means what? 1.05 LA1. 1.05 LA1 means you'll get this like 1.05 into 1.1. Anybody tell me this number how much? 1.05 into 1.1. 1.155. Okay. You tell me what is the formula for LA2? LA2 formula 0.2 ln of D2 by R dash. D2 by R dash. Let me write in the next slide. Next slide. LA2 formula is 0.2 natural logarithm D2 by R dash in terms of millihenry by kilometers. Now, already we have LA1 formula and we have LA2 formula and we have LA1 number, LA2 number. And we have to find out the relationship between D2 and D1. We have to find out the relationship between the D2 and D1 values. Okay, so let's move. Let's take that LA2 minus LA1. Let's take LA2 minus LA1. Thereby you get ln of D2 by R dash minus ln of D1 by R dash. There you get ln of D2 by D1 and we'll try to get the D2 and D1 relation. Okay, so let's say here LA2 minus LA1, which will be like 0.2 ln of D2 by R dash minus 0.2 ln of D1 by R dash. Okay, so LA2 number 1.155 minus LA1 number is 1.1. LA1 number is 1.1. Okay, so that is equals to, you take this resultant, what you get now? 0.2 ln of D2 by R dash by D1 by R dash. R dash will be cancelled out. You will get this 0.2 ln of D2 by D1. And this resultant you get like 0.055. And ln of d2 by d1, d2 by d1. So it will be like 0.055 by point. I think you may get this number 0.275, 0.275. And you can get d2 by d1 from this now. How much is that d2 by d1? d2 by d1 is equals to e power 0.275. E power 0.275. And how much is the value of d2 now? d1 into e power 0.275. So that will be like, I think 1.316 times of d1. So distance between the conductors was increased by 31.6%. Distance between the conductors was, has to be increased by 31.6% to have an increment of inductance by 5%. To have an increment in the inductance by 5%, we have to increase the distance between the conductors by 31.6%. Okay. So I think all of you getting this one. Yeah. See, how much is the percentage increment in the inductance we had? Only 5%. But how much is the distance increment here? 31.6%. See, the observation what you have to make here is, with respect to increment in the distance, inductance value definitely increases. Inductance value definitely increases. But the increment in the distance is very, very high compared to the increment in the inductance what you got. That's the observation what you have to make here. All of you getting? So that is due to one very simple reason. Definitely, if D is decreasing, obviously inductance value is going to be decreased. Yeah. Listen, please, listen. I'm taking up some numbers here. Just observe why it is happening in that panel that I am going to explain to you. Just look here. For example, I'm asking some values in a sequence. Just look. ln of 200. ln 250. ln 300. ln 350. ln 400. Can you please tell me these numbers? ln 200, how much? ln of 200. Calculate these values. 5.3. ln 250. ln 250. Tell me in a sequence. 5.5. ln 300. ln of 300, how much? 5.7. ln of 350. 5.85. And this number is close to 6. That ln of 400 is close to 6. What's the observation we can make from this now? What is the observation we can make from this? See, inside the natural logarithm, we have numbers like 200, 250, 300, 350, 400. But how is the natural logarithm of that value? He is coming more or less same, right? Natural logarithm of that value is coming more or less same. 5.3, 5.52, 5.7, 5.85, 6. You don't have a great change. You don't have a great change in the natural logarithm value. Don't have a great change in the natural logarithm value. That's the reason why we are going to have this inductance value coming more or less same. I will explain you. Just look back to this one. Look back to this one. See, 1.1 is the inductance now. 1.1 is the inductance value. If I substitute 1.1 in this, 1.1 by 0.2. 1.1 by 0.2, 5.5. It's 1.1, it's 0.2. So it will be 5.5. So if it is 5.5, what is d1 by r dash number? d1 by r dash number may come very close to 250. D1 by R dash number may come very close to 250. See, even though that value 250 was increased to 350, 250 was increased to 350, natural logarithm value is not going to be greatly affected. See, this natural logarithm value, after all, multiplied with 0.2 will give the inductance, right? Multiplied with 0.2 will give the inductance. Following all of you? Yes. So my intention is to tell you, even though you have a good variation in the value of d by r dash, still the value of inductance will come more or less same. Still the value of inductance will come more or less same. Following all of you. Now tell me, I have a 11 kV line and I have a 33 Yeah, sorry, the video audio problem. Yeah, you observe this one. So for 11 kV line and 33 kV line, if you say, inductance formula will be same. Inductance formula will be same. And we have a change in the value of d by r dash. D by r dash. Because of the change, we might expect a change in the value of inductance. But you know, even though the value of d by r dash is heavily changing, inductance value will be more or less same. Inductance value will be more or less same. All of you understanding this one? So that for any transmission line, for any transmission line, inductance value will be in the range of 1 to 1.2 millihenry by kilometers. Okay. So I'll say for any transmission line, single circuit. Moreover, I'll write this one, single circuit transmission line. Any single circuit transmission line, inductance per phase will be around 1 millihenry by kilometer to 1.2 millihenry by kilometer. 1 millihenry by kilometer to 1.2 millihenry by kilometers. Okay, so I will be stopping the class at this point. Tomorrow we have a schedule from 7 a.m. to 1 p.m. Tomorrow we have from 7 a.m. to 1 p.m. A doubt session I will take tomorrow. Doubt session also I will take tomorrow. I'll spend some more time in tomorrow class at the end. Please kindly cooperate. I am sorry. Tomorrow only we have this timing. Monday we don't have class. Monday we don't have class. Okay. I am showing previous slide. So if you are writing, please go through it quickly. So I'll take doubt session tomorrow. Thank you. I am closing this one. Can I close?